Hey guys, Assalamualaikum warahmatullahi wabarakatuh. I hope you guys can hear me loud and clear. Somebody please respond.
Yeah, doctor.
Thank you very much. Okay, a very good morning to everyone. You have submitted your mini project. Congratulations for in having completed it. The coordinator of that mini project is Dr. Jamaroliza. So she will be dealing with the marking, and I will be only taking from her marks given to you guys. Okay, but I have some inputs from you guys regarding your members. I will take that also into account. Okay, guys. Okay. So today is this week is our last week. By next week, you will have a week of study leave. After that, you will have your final. I did not look at what's the date for your final for this energy balance, but I will let you guys know. But anyway, we still have a topic in chapter 9 that we need to cover, which is thermochemistry of solution. So I will stop sharing this QR code for those who uh, join us later. You can request for it towards the end of the lecture. I hope I can give you another quiz by tomorrow. I hope, or else we only have one quiz throughout the whole semester, which is, well, either I take that into account or not, I'm not sure. Yeah. Anyway, let's proceed with what we have. We have this topic in chapter 9. I'm not sure what what is it? 9.5C, if I'm not mistaken. It's thermochemistry of solution. It's related to what we have covered last week. Last week we touched on heat of mixing, yeah, or solution. Let me change this color. I prefer it to be red. And so heat of solution or mixing, we have managed to get that value from table B11. The symbol that we give it is delta H with a cap at standard temperature of 25 with a subscript S, that is for solution. The bracket R is equal to mole of your solvent, which is normally water, per mole of your solute, which is the liquid or the gas or the solid that is being mixed with the solvent. So that no, if you look at if you look at table B11, yeah, this is how it looked like, and the reference state is at 25, or the value in this table is at 25. Okay, this is your R. This is recalling back what we have covered last week. You have for hydrochloride, you have for sodium hydroxide and sulfuric acid. The unit is kilojoules per unit mole of your solute. Remember that. So you can get it, but from looking at the value of R, you should be able to get your heat of mixing or your heat of solution from this table. And if you take note that at the very bottom, there is an infinity value of R, meaning that your solution is having an infinite volume of water. The amount of solute is very, very little. So when you want to find that heat of mixing or solution, you have this superscript infinity, implying that there's so much of your solvent compared to your solute. So the value is at the very bottom. So you can get that from this table, and also you can get it from appendix B1. Okay, let's look at appendix B1. This is appendix B1, and for infinite solution, the symbol for heat of formation, sorry guys, heat of formation is actually aqueous. You cannot see it now. I saw one. This is one of it. aqueous. Okay, that is for copper sulfate, cupric sulfate. Okay, there's the aqueous there. The aqueous implies that it is at infinite dilution. Okay, that's one. Let's go back to our note. You can also get it from other sources. In this case, I think it's from Perry Handbook. Okay, so if you look here, could hardly see your delta heat of mixing, enthalpy of mixing, the molar enthalpy of solution at infinite dilution. That means there's a lot of your solvent compared to your solute. Okay, so the solute listed here, there's a lot of it compared to the one that is given in B11. There's only 3. Over here, you have a lot. So this is a very useful table to use. And another form of data that you can use is from this graph. Unfortunately, there's only 2 of it. This is for lithium, not mistaken, chloride, and this is hydrogen chloride gas. So depending on the mole of water, this is actually R. This is actually R, and this is your enthalpy of mixing. That's your enthalpy of mixing. Okay, so you can get in a table form or in a graph form. Then this is another graph that we have used last week. Enthalpy concentration. This is for sulfuric acid versus water. And you will know the reference state. Your water is pure water at 32 degrees Fahrenheit, and your solute is pure sulfuric acid at 77 degrees Fahrenheit. That is your reference state. So if you're using this graph, you need to follow that reference state. The same case for this graph. I'm not sure what is the reference state, but all you have to do is look at when it is 0, you should be able to know what is the reference state. When the enthalpy is 0, you should be able to know what is the reference state. As you can see here, that is 0. So if you projected it on the other side, that is also 0. Okay? So the enthalpy is 0 at the reference state. So it's easy to know what is the reference state. Okay, there's a typo error here. That this graph is for sodium hydroxide. So if you have that this not, please correct it. This is for sodium hydroxide. Your graph look a bit different from sulfuric acid, but it's actually the same in terms of mass fraction. You have over here mass percent, and in this graph you have mass fraction. You have your temperature isotherm, and over here you also have your temperature. This is the temperature given. Okay, and then your enthalpy. That's your enthalpy. But both of them are in BTU per pound mass solution. This is also BTU per pound mass of solution. So it's the same thing. Okay? It's just that it is referring to sodium hydroxide instead of sulfuric acid. Again, you should be able to locate the enthalpy if you look at 0. I'm not sure what is the enthalpy here. Pure water. This is pure water, but your pure sodium hydroxide, you cannot locate it because the mass fraction stop at 0.75. So you can find the pure sodium hydroxide based on this graph. Yeah. Okay, now this is what we're supposed to look at today. Okay, so this is from chapter 9. You're going to find the heat of formation of the solution. That's what is different from last week. Last week, we were looking at the heat of mixing of the solution. But this week, we're going to look at heat of formation. Heat of formation, as we know, the subscript is F. This is the symbol. The same thing as what we have been looking so far, heat of formation. Superscript 0 because it is at 25 degrees C. That's your subscript solution. We're looking at solution. So if you look at this block diagram, you start from the elements of your solute. You start from the element of your solute. You form it first. You form the solute first. You form the solute first at 25. So this is your heat of formation of solute. you have the element, you start from the element, you form the solute. So you have the heat of heat of formation of the solute. After that, you mix it with your solvent. So this is your heat of mixing. You form your solute from the elements. You mix it with the solvent again at the same temperature, 25. Then you end up with your solution at 25. So this equation is the heat of formation for that solution at 25. Why is it 25? Because this is the standard temperature. Okay, that's the standard temperature at 25. So you can get your heat of mixing, this part, from table B11, that is the one that we have discussed last week. Your heat of formation of the solute, you can get from table B1, okay, and you end up with your heat of formation of the solution. Why do we need the heat of formation of solution? You need it when you want to calculate the heat of reaction. When you have a certain reaction written where you have aqueous solution, then you need to find the heat of formation before you can proceed to get the heat of reaction. Okay, so you need, this is what we're going to cover. We're going to get the heat of formation of the solution. And the temperature is always at 25. Okay, guys, the temperature is always at 25. So in this case, have a look at this example. You have this equation, and let me tidy up a bit, because everything seems to be around it. Okay. So in this example, you have this reaction. Okay. This is your element. That's your element. That means you're going to form solute here. Once you form solute, then you mix it with water. Then you get your solution. Okay. So what is the heat of reaction for this example? Okay. So what you have to do is you follow this equation that I have highlighted in yellow. Okay. You get your solute. Your solute will be, this is your solute. Your solute will be this compound. Okay. You get your heat of formation from appendix B1. Okay. That is for lithium chloride. And you will get your heat of mixing from the graph from lithium chloride. Depends on what is the value of R. Depend on what is the value of R, then you should be able to get your heat of solution. So for lithium chloride, you can use this graph, that is this graph, okay, lithium chloride, depending on what is the value of, depend on the value of R, you should be able to get the enthalpy. That's the enthalpy on the left-hand side, on the y-axis. So this is your graph for lithium chloride. So based on that graph, you should be able to get your heat of solution or your heat of mixing. So once you have that value, you sum it up, you will get your heat of formation of that solution, which is actually, for this case, for this example, is your heat of reaction. So this is going to be your heat of reaction. Because you are forming this solution, actually. You're forming this solution, which is lithium chloride with 12 mole of water attached to it. So that is your heat of formation of that solution. So that's how you get it. So it's like I have it over here. Your heat of formation for your mixing is from table B11. Your heat of formation of your solute is B1. Okay, so far, okay, just based on this equation, you just stick to this equation, you should be able to get the heat of formation of your solution. But remember, you're doing it from the element. You're starting from the element, so you need to get the heat of formation of solute first. And all of this is occurring at 25 degrees C. So let's look at an example. Before that, your heat of formation of the solution, heat of formation of the solution, you can get it also from appendix B1. It's like I listed just now. This is one of it, This is one of it. There's another one, Okay. The heat of formation of the solution at infinite dilution. at infinite dilution. R is equals to infinite. You can get it directly from table B1 instead of using the equation here. Instead of using the equation, you can get it directly from B1. Yeah. So let's look at this. Do you have what compound is this? You have, let me see. This is ammonium sulfate. So the heat of formation for it is minus 1173.1, which is from that graph at infinite dilution. That is your heat of formation. Okay, let's look at an example. This is one example. Calculate the heat of formation of hydrogen chloride in 5 mole of water for part A. Your solute is hydrogen chloride. Your solvent is water. Your R in this is actually 1 mole of hydrogen chloride in 5 mole of water. It's not listed as 1 mole, but it's understood as 1 mole of hydrogen chloride in 5 mole of water. So your R is supposed to be mole of solvent per mole of solute. So your solvent is water, so that's 5 mole divided by 1 mole of your hydrogen chloride, that will be 5. Okay? So if you want to get the heat of formation of your hydrogen chloride, will be aqueous. So you will use this formula, the one that is highlighted in yellow just now. That is the heat of formation of your solute plus the heat of mixing of your solution, which is R equals to 5. That's the value you just calculated just now. Okay, so now let's look at our hydrogen chloride from table B11. We're going to get that value. From table B11, 5 mole of R is equals to 5. So let's go to table B11. Hydrogen chloride. Going to erase this. That is hydrogen chloride. R equals to 5. That's 5. That's the value that we want. Negative 64.05. That is the heat of mixing for our hydrogen chloride when the value of R equals to 5. That's minus 64.05. So that's the value I will substitute inside the equation. Okay, that's 1. I need to find that from table. This is B11. This is B1. I need to find the heat of formation of hydrogen chloride gas. This is actually a gas. And this is your liquid water. So we're going to look at appendix B1 for hydrogen chloride gas. That is my appendix. Yeah. So hydrogen chloride. Okay, there. I have it highlighted over here. That is hydrogen chloride. And the gas, the heat of formation of that gas is negative 92.31. That is the heat of formation of hydrogen chloride gas, negative 92.31. So I'm going to go back to my example. That will be negative 92.31. So I'll end up with the heat of formation of my hydrogen chloride aqueous solution. So if you do the calculation, let me calculate it. 92.31 minus 64.05. I made a mistake. 0.05. So you end up with negative 156.36 kilojoules per mole of your solute. It should be per mole of your solute because this is aqueous. That is your aqueous solution for hydrogen chloride. So that is per mole of your solute, and that answer is the same as the answer given here. So that's how you use this equation to get the heat of formation of your aqueous solution. And let's do another example, which is part B. For part B, it is hydrogen, your solute is hydrogen, sulfuric acid, which is liquid. Let's undo that. Solute equals to sulfuric acid, liquid, and your solvent, as always, is always water, unless stated differently. That is always water. Now it's liquid. And what is given? Infinite dilution. So your R is equals to infinite dilution. Yeah. So if you follow this equation, your heat of formation for your sulfuric acid aqueous is equal to your heat of formation of sulfuric acid liquid plus the heat of mixing of your solution, sulfuric acid solution, subscript S, R equals to infinity. Right? So if we look at table B11 for that part, for sulfuric acid, sulfuric acid. So where is sulfuric acid? Sulfuric acid is on the here in the last column on the right hand on the rightmost hand side, and at infinite dilution, that is infinite dilution. That is your sorry, I got it wrong. Okay, that's the marker. Okay, minus 96.19. So that's minus 96.19. So I'm going to substitute that value. Plus minus 96.19. My heat of formation of sulfuric acid, I should get that from B1. So that's liquid sulfuric acid. So let's go back to our appendix. B1 for sulfuric acid should be S. Yes, sulfuric acid. Yeah, there you have it. Sulfuric acid. I have highlighted it. Let me tidy up a bit. Here you can see that this is sulfuric acid and heat of formation. You have two values over here. This is the one that we want. The one in the bracket liquid. So that is negative 811.32. Negative 811.332. So that's the value I will substitute in the equation. So you end up with your heat of formation for your sulfuric acid aqueous solution at infinite dilution is going to be the sum of these two values. So we do the calculation. That is going to be your final value for the heat. Sorry, that should be 7 for the heat of formation. That's kilojoules per mole of sulfuric acid of your solute. So let's have a look at the solution, the answer. Okay, it's the same as what we have. That's the answer. And if you take note, just now when we were looking at the appendix, that value is also listed for hydrogen chloride. Okay, that's the value. Let me use a different marker. So that's the value here. That's the value that you can easily get from appendix B11, B1, instead of calculating it according to that equation. Okay? Unless it's not available in B1, I keep on repeating the same mistake. This is appendix B1. Okay? Unless it's not available here, then you'll be using that equation to calculate the heat of formation of your solution. So this is the heat of formation of your solution at infinite dilution. If you have a value of R that is not infinite, then you cannot use this equation, this value of negative 907.51. This is only when R is equal to infinite, then you can use that value. Right? So even though it is given in appendix B1, but if your R is not infinite, then you cannot use that value. Okay, guys? So any questions so far? what we have done is just using that equation to get your heat of formation. Let me generalize this. This cannot be hydrogen chloride. It can, oh dear, my God, I already deleted heat of formation of solution. Okay, this case, I need to erase this because that's just R, wood here. That's just R. That is the general equation. That's the general equation. Any questions so far? Anybody? You guys very quiet. Are you guys okay? Everybody seems to be stressed out. It's already the end of, the end of the semester. Final is coming soon. Are you guys okay?
Yes, clear, Doctor.
Thank you very much, Sulaiman. It's been tough. The whole semester, the whole year has been very tough for you guys with this online learning. The same as the lecturer, we are also being stressed out with this online learning. It's not as as enjoyable as having face-to-face lecture. It's easier face-to-face. You meet the student, you get to know the student. Right now, I just know you guys by name. I don't know you personally, so it's not as good as having face-to-face lecture. I hope this whole thing will be over soon, but by the look of it, I'm not sure when it's going to be over for Malaysia. Okay, so just hope for the very best. Anybody, any questions? Any question? We're just looking for the heat of formation. Why do you need the heat of formation? Because you need to calculate the heat of reaction. Why you need heat of formation? Because you want to calculate the energy balance. Because your heat of formation can be used to get your enthalpy. Okay? If you set your reference state to be 25, then your heat of formation. Okay, let's look at that later on. We have a few examples that we can look at. Okay? Better not confuse you guys. Any questions? Anybody? Okay. So that's a very simple example. It should be clear, very clear. So now let's have a look at, I'm not going to do this example. Actually, you can look at the solution yourself. This is one example whereby you're going to calculate the heat of neutralization. So I'm not going to use this note over here to do the example because the space is too little. I'm going to look at it here. I'm going to solve it here. Calculate the heat for part A. Calculate the heat of neutralization for this between hydrogen chloride and sodium hydroxide. You guys have already actually done this in your mini project. You have the neutralization reaction there. So this is actually for some of you guys, you already know how to do it. Okay? So given that in the statements said that the heat of solution for sodium chloride is 4.87 kilojoules per mole of sodium chloride. So what do we have here? We have hydrogen chloride. This is the reaction. Okay. It did not say anything about the number of mole, anything. So you're going to assume that everything is going to be at infinite dilution. Because there's no mention of the number of mole, so you cannot calculate R. So you're going to assume that R is going to infinite dilution. So if we write that equation over here, and hydrogen chloride equals, it is mentioned that the reaction between dilute, okay, this already mentioned dilute. So that means obviously that is at infinite. We're going to assume it is at infinite. It's very infinite dilution. So R equals to infinite. Right? Plus your sodium hydroxide, which is a base, equals R equals to infinite. I'm hearing R so your salt being formed equals R equals to infinite. You have water in the form of liquid. So that is your reaction. So actually the question asks for your heat of neutralization, and that is actually the heat of reaction. For this reaction, it is neutralization. So what is the heat of reaction? So that's the question. So now, in order to get the heat of reaction, remember you guys, you know this equation already. You did it in your test 3. So this is, we're going to use heat of formation. We're not going to use heat of combustion. So according to heat of product formation, that is product, your stoichiometric coefficient of every component, in this case is for the product, your heat of formation of that component minus your reactant, because we are using the heat of formation, so product minus reactant. Unless you're using heat of combustion, then it's the other way around, reactant minus product. Okay, so now let's list down every component that we have in the product. The product is here. We have stoichiometric coefficient 1 and 1. Every chemical involved in this reaction have a coefficient of 1, so it's easy, that way it's very easy to remember. So that is the heat of formation of your sodium chloride aqueous, R equals to infinite. Or if you don't want to write that, what you can do is you can write it in a different way. Okay, aqueous, or you can say just aqueous. Can also write it as aqueous because it's understood that it's at infinite dilution. So the other compound which is in your reaction, in your product, sorry, is water. The heat of formation of water, that's liquid. So that is this part from your product. So for your reactant, you have two reactant minus, you have your coefficient for the hydrogen chloride. So heat of formation of hydrogen chloride. In this case, you're going to have aqueous at infinite dilution. You don't need to write the R equals to infinite. It's understood. Plus 1 heat of formation of your other component, which is sodium hydroxide. That is aqueous. Okay. So this is based on the equation I have listed here. So now what you have to do is just get the heat of formation of all these components. If you can get it from appendix B1, that's very good. So let's see whether we have what are the values that is available. We need sodium chloride aqueous. We need the heat of formation for water, liquid water, that obviously is going to be available in appendix B1. You have your heat of formation of hydrogen chloride aqueous. You know that is available in appendix B11 because you have that infinite dilution at the very bottom of the table. And lastly, you have your heat of formation that you need to look up. Sodium hydroxide is also from appendix B11. It's available in B11. So let's do the bottom two first. Look at appendix B11 for sodium hydroxide and hydrogen chloride. For infinite, oops, I need to go to my notes. Okay, where is my, okay. Let's look at B11. Okay, this is B11. If you look at this, your hydrogen chloride is here. Okay, that's hydrogen chloride. That's hydrogen chloride. And infinite dilution, that's the value. And I'm going to erase this. The other value that is of interest that we want to find is sodium hydroxide. Okay, so based on these two values, we are going to substitute it in our example just now. So let me see whether I have it written here. Plus minus. Wow, this is 42.89. That guys, sorry guys, I made a mistake here. This is your heat of solution, not the heat of formation. Okay, this is delta H. This is it, delta H of solution, not delta heat of formation. We need to look at appendix. Okay, now let clarify this. Let make it very, very clear. The value that I set over here is actually this value, heat of solution. It's like it mentioned here, solution and mixing. Okay, that is the heat of formation. So all the heat of formation should be in appendix B1, not in this table B11. This is if we're going to calculate it using this equation. Let me clarify this, because I don't want you guys to be confused. If you're going to use this equation to get your heat of formation, then that value that we're going to get from this table is going to be the last term here. Okay, that should be it. Huh? Better not write infinity. And it could be any R value of any R. For this case, for this example, R is equals to infinity. So this is the equation. So your heat of mixing you can get from appendix B11, just like I mentioned just now. But your heat of solution, you can get it from B11 if it's available. Okay, so let's look at B11, not this not B11, sorry, B1. B1 is your heat of formation. B11 is your heat of solution. So get that clear. I need to get it. I need to correct myself. Okay, B1. So this is B1. So heat of formation is over here. That is your heat of formation. So in this case, we're going to look at hydrogen chloride. Let's look at hydrogen or sodium hydroxide. We have sodium hydroxide over here. Let me erase the others so that you can see where we are looking at. This is sodium hydroxide. Okay. This is the aqueous. That's the heat of formation. The aqueous, the heat of formation. Let me repeat. I got you guys confused. If I don't, I need to clarify this. The heat of formation, the aqueous you can get from B1. The heat of mixing you can get from B11. So get that clear, because I might be confusing you guys for the mistake that I have mentioned just now. So this is your heat of formation of sodium hydroxide, having that aqueous term there. So the other one is hydrogen chloride. So let's look at hydrogen chloride. I hope it's available. Where is hydrogen? Okay, hydrogen chloride. Okay. No, it's not available. Why? Because you don't have the aqueous term there. You just have the gas. You just have the solute, the heat of formation of the solute. So the heat of formation of the solution is not given for hydrogen chloride. You only have for sodium hydroxide. So let's try to look at whether we have for water, heat of formation of water. We need water. Yeah, water is here. The heat of formation of water, liquid water, that's the value, minus 285.84. So we're going to list that down. We're going to list it down in our example. Just now we have for sodium hydroxide, negative 469.4 kilojoules per mole. Yeah. The other value that is listed there in the same row is for hydrogen chloride in as a solid. That value is 426.6. Let me, okay, that's kilojoules per mole. Let's go back to our appendix. I need to show you guys that. Hydrogen chloride, sorry, not hydrogen chloride, sodium hydroxide. And the other value is this. That is 426.6 for the solid. For the solution is the one that I highlighted in green. That is the solution. The solution that is being formed at infinite dilution. So that is this value. So let's go back to the example. I got that listed down. Now for hydrogen chloride, we don't have the value listed as aqueous. So we need to calculate it using this formula. For hydrogen chloride gas plus the hydrogen chloride for mixing. Not F, S. Should be S because it's for mixing. R equals to infinite because this question asks for infinite. So for that value here, we can get it from appendix B1. Hydrogen chloride. We did mention it just now. Okay, this is the value. which is minus 92.31 for your gas. Okay, so let's put that value inside our equation. That is equal to minus 92.31. And for the heat of solution from appendix, this is B1, this is B11. For heat of solution from B11, I need to go to appendix B11. I'm going to use my notes. Okay, the one that I just make a mistake when I mentioned that you can get the aqueous from here. No, this is only the heat of mixing or solution. So for hydrogen chloride, that's the value at infinite dilution. So that is going to be negative 75.14. You will put it inside the equation just now. So this is only the H of solution, guys. Sorry, not F. I keep on repeating the same mistake. S, subscript S. Solution, not formation. Yeah, so that's minus 75.14. Go back to our example. That's plus minus 75.14. So you should be able to get the value. When you have done the calculation, you will get negative 167.45. That is for hydrogen chloride aqueous, mole of hydrogen chloride. This is mole of sodium hydroxide. Yeah, the same thing over here. If I since I don't have space, I cannot write it, mole of sodium hydroxide. So for water just now, we did look it up in appendix B1. That value, we noted it was negative 285.84. That's kilojoules per mole of your water. Yeah. So now sodium chloride. Not sure whether we can get it directly from B1. So let's have a look whether it is available in B1 as aqueous. Sodium chloride. It should be somewhere here. This is M. The sodium chloride is here. Let me highlight it. That is sodium chloride. And the value given is not in aqueous, but solid. So that is the solid heat of formation of sodium chloride in a solid form. It's negative 411.0. That is for solid. It is not for your aqueous. There's nothing aqueous is not listed here. So you need to use the equation that we have used previously to calculate your heat of formation for the solution. Let's put that here. Use the equation that the heat of formation of your sodium chloride solid, that's C crystal, plus your heat of solution from appendix B11. So in this case, your R is equals to infinite. So that is B11. That is the value that we just look at from B1. So that value, it is minus, what did I mention just now? 411, isn't it? Right. So we're going to get from B11, the heat of mixing for sodium chloride. So let's look at our table B11. For sodium chloride, is there sodium chloride here? No. Sodium chloride is not for sodium chloride. So, but if I'm not mistaken, it was given in the statement of the problem. It was given. Okay, here it is. The heat of solution, sodium chloride is 4.87. So that means we're going to use that value for the heat of solution, 4.87. So let's put it down here. We're not going to use this value from B11 because it's not available in B11. And so we're going to add that value 4.87. It's given in the statement of the problem in the example. So once you calculate it, you get this value, 406.13 kilojoules per mole of sodium chloride. I have enough space to write there. Oops. Okay. So we have everything here for in order to get our heat of reaction. So now I'm just going to mention it to you guys. For that part, you use this value. Okay. Put that value, substitute that value there. That is the heat of formation of sodium chloride. For the heat of formation of liquid water, that is the value. We're going to substitute it there. For the heat of formation of hydrogen chloride, this is the value. We're going to substitute it there. Okay. And lastly, for your sodium hydroxide, we're going to put that value, the aqueous value. Going to substitute it there. Everything is there. But now if you substitute it, we calculate that value. The heat of formation, which is happen to be the heat of neutralization. So for sodium chloride, is minus 406.13. For water, minus 285.84. Now minus for the reactant, you have for hydrogen chloride minus 167.45, and for your sodium hydroxide minus 469.4. So everything is there, and when you do the calculation, let's see what did I get. When I do it, I got minus 555.12 kilojoules per mole. That is my heat of reaction for the neutralization process as listed according to this equation here. According to this equation here, that is my heat of reaction. Minus 55.12 kilojoules per mole. Let's check the answer. Here is minus 55.03. Well, there's a slight error in the value after the decimal point, but it's obviously is minus 55. Right? So that's how you go about to calculate your heat of reaction. Again, I need to mention this. Your heat of formation can be calculated according to this. Your heat of formation of the solution can be calculated according to this equation. You got to get the heat of formation of the solute from appendix B1, and the heat of mixing, you can get it from, if it's available, from your appendix B11. And you can get also that if it's available from appendix B1. It should be listed as heat of formation aqueous of your aqueous solution. Aqueous solution. You can get it directly from appendix B11. That's how you solve for heat of formation. Either you use this equation, or you can get it directly from appendix B1. That is like what we did just now for sodium hydroxide. We did this for sodium hydroxide. We got this value directly from appendix B1. Okay guys, any questions? We're just calculating the heat of reaction. You need to know the heat of reaction because when you want to calculate the energy balance using the heat of reaction, you got that external reaction, your heat of reaction. Then you have this term out, your product from the molar flow rate with that of the enthalpies, minus in the product of your molar flow rate with that of the enthalpies. So you need that information in order to solve for your amount of heat supply or amount of heat removed. So that's one way of doing it. And in fact, you can also calculate your enthalpy from the heat of formation. Okay. So any questions on this example, the part A? Any questions? No questions? I hope everything is clear. Okay. I hope everything is clear. Do not get confused by my mistake just now. B11 is for the heat of mixing or the heat of solution, not for the formation of the solution, not for the heat of formation of the solution. Appendix B1 is for the heat of formation of the solution. So please get that right. Okay, for part B, since there's no question, I'm going to proceed with part B. The question asks for the standard heat of reaction between hydrogen chloride gas and solid sodium hydroxide to form sodium chloride and liquid water. It's according to this equation. What's the difference between the previous equation? For part A, you have that aqueous term there, you have that aqueous term here, you have that aqueous there, and that's liquid water. For part B, you have gas, you have solid, you have solid, you have liquid water, as same as over here. The only difference is that for part A, you're forming the solution. The aqueous is here. There is the aqueous for hydrogen chloride. There is the aqueous for sodium hydroxide. There is aqueous for sodium chloride. Over here for part B, there is no solution at all being formed. You're just reacting the gas of hydrogen chloride with the solid of sodium hydroxide, forming the solution, the crystal of sodium chloride plus liquid water. There's no solution being formed at all. So this is completely different. You're not going to use that formula where you have the heat of formation of the solution equals to the heat of formation of the solid plus the heat of mixing. You're not going to use it at all. You're just going to directly get this value, these values, you're going to get it directly from appendix B1. No aqueous term at all. Okay, so let's see what we have so far. I'm going to change the marker, the color of the marker, because I'm going to distinguish from what I have highlighted before. The heat of formation of water. I have over here the heat of formation of water. Yeah, liquid water. The heat of formation of hydrogen chloride gas. Hydrogen chloride gas. The heat of formation of hydrogen chloride gas. That's the symbol, and that's the value. Yeah, from appendix B1. It's gas. Only gas, not the aqueous. Now, the heat of formation of sodium chloride. The heat of formation of sodium chloride, that is the symbol, and that's the value from appendix B1. Okay, and lastly, the heat of formation of sodium, okay, that's sodium chloride. That's completed it, is it? Okay, the heat of formation of sodium hydroxide, heat of formation of sodium chloride. Sorry. That is the heat of formation of sodium chloride, crystal, -4 to 6.6. So the values that we have already got for that part A is going to be used for part B. Okay, so let's do part B. The equation is just straightforward according to this equation. I'm going to write that again. Hydrogen chloride gas, the sodium hydroxide solid, denoted as crystal, going to form sodium chloride solid plus liquid water. So that's the equation. So the question asks for what is the heat of reaction. And let's look at the question. What is the standard heat of reaction? That's the standard heat of reaction. So now, if we guys all know how to do this using the standard heat of formation, the product, the stoichiometric coefficient, heat of formation, minus the reactant, stoichiometric coefficient, and the heat of formation for the reactant. So all of your components in this reaction has 1. The coefficient is 1. So that's very easy to remember. So that's just put in the heat of formation. For the product, we have product sodium chloride solid. The heat of formation of liquid water. I'm not going to write 1 in front of it because it's understood there is 1. Okay, heat of formation of liquid water. That's your product. Now minus the reactant. The reactant is going to be the heat of formation of your hydrogen chloride gas plus the heat of formation of sodium hydroxide solid crystal. Now let's get the values from the previous example. Is equal to heat of formation of crystal sodium chloride, the one I highlighted in red, that's the value, minus 411 plus of liquid water, we have that value here, minus 285.84, close the bracket, that is for the product. Now for the reactant, we have the heat of formation of hydrogen chloride gas hydrogen chloride gas, that's the value, minus 92.31, plus that of sodium hydroxide crystal, we have it over here, minus 426.6. Everything is there. So do the calculation. Your heat of formation, your heat of reaction, once you do it, happen to be minus 177.93 kilojoules per mole. That is the heat of reaction for the second part of the example. And if let's have a look at the solution given, also same value, minus 177.93 kilojoules per mole. So any questions? For this second part, it's just straightforward getting it from appendix B1 because you're not looking at solution, you're not looking at aqueous solution, you're looking at gases and solid and liquid. So it is just straightforward heat of formation from appendix B1. You're not going to use this equation, you're not going to use that equation because there's no solution at all involved in the second part of the example. It's just solid, liquid, and gases and gas. So that's the difference between part A and part B. For part A, you have the equation. You have the equation written here. You have aqueous. You have aqueous. You have aqueous. That means you are forming solution. So you need to get the heat of solution. Any questions? The difference between A and B? Any questions? Anybody? Are you guys still with me? I'm quite surprised nobody is responding. Too tired, still sleepy, guys? Too early for you guys? Especially those in Qatar, in Saudi, and also in Yemen. It must be very difficult having lecture in the very early morning when everybody is sleeping and you are all alone awake. It's just too sleepy, I guess. It's too hard for you guys. You are not. We don't have the same time. You are in a different zone, different time. Okay, guys. Any questions? Anybody? Any questions? Nobody? No questions? Okay, let's give it tech 5. Now we show the QR code. Come back at 9:17. For those who haven't scanned, I will share you guys the QR code. I prefer to give you guys the break because I'm sure some of you haven't taken your breakfast yet. Some of you are still in your bedroom, still in your pajamas. So you need to refresh. Okay, take 5, please. I'm going to share you guys. Okay, guys, welcome back. Hope you guys are comfortable now. Have taken your breakfast, or still taking your breakfast, having the lecture at the same time. Okay, let's look at another example. If example from the, not really an example, a problem from the back of the textbook. This is according to the third edition, the numbering. Let's share it. Why is it? Okay, there you go. It's problem 944 according to the third edition. This is not from your notes. You have a dilute sulfuric acid solution at 25 degrees C. You're going to mix it with ammonia, absorb ammonia in it to form ammonium sulfate. This is the equation. Yeah. Your ammonia enter at 75 degrees C, sulfuric acid at 25 degrees C, and the solution itself will be also at 25 degrees C. Question asks, what's the amount of heat that must be withdrawn from the entire unit if you're going to form 1 mole of the solution per mole of the solution? That means 1 mole of the solution. Okay? First thing that you need to do is draw your block diagram. Okay. Over here, we have 2 inlets. Your inlet is going to be 1 mole. Based on this equation here, based on that equation, we're going to form 1 mole, and we're going to assume that the reactant, they are supplied according to the stoichiometric coefficient. So that means you need 1 mole of sulfuric acid and 2 mole of ammonia gas. So we're going to, based on that stoichiometric coefficient, that's the amount of input that we're going to supply. We're going to put into the product, into the unit. So what we have here, we have 2 mole of sodium, of ammonia gas. Okay, that is coming in at 75 degrees C. Right? Next, we're going to mix it with our sulfuric acid. So we're going to have 1 mole of sulfuric acid, aqueous. That is aqueous. There's no mention at all. Yes, there is a mention of dilute sulfuric acid. So that is going to be the value of R is equals to infinity. We're going to form sodium sulfate. So the question asks for 1 mole of sodium sulfate. 2SO4, and it is aqueous, so it's going to be a dilute aqueous solution. So R equals to infinite. So what was need to jot down the temperature? The sulfuric acid is entering at 25 degrees C, and your solution is being formed at 25 degrees C. Okay. Question asks, what is the amount of heat that need to be withdrawn? In kilojoules. That's the question. Well, our basis, every time you have any calculation, even though you're not going to do any material balance because it's already the material, the amount is all completed. You have every stream having the amount listed, so you don't have to do the material balance, but still just write down the basis. 1 mole of your product, which is sodium sulfate. First. So that's your basis. Now, we need to find the Q. If you do if you write the full equation, you don't have to dot over there because it's just amount, it's not flow rate. Your kinetic energy, your potential energy equals to Q plus WS So we need to cancel, drop the terms for kinetic energy, potential energy, and shaft work because there's not moving parts. There's no change in elevation. There's no change in velocity. So cancel that off. You end up with your Q is equal to the change in enthalpy. And since this involves reaction, there is a reaction here. So you're going to use it there's two ways of doing it. One of it is using the heat of formation. The other one is heat of reaction. So we're going to do it both. This is using the heat of reaction. That means you have the heat of reaction there. Out the product of your flow and the enthalpy minus in product of your amount with the enthalpies. So that is according to heat of reaction method. That's the heat of reaction method. The other method, according to the heat of formation, is just simply out the amount times by the enthalpies minus in the product of the amount times by the enthalpy. So this is according to heat of formation method. So we're going to do both methods, but we're going to do heat of reaction first. Okay, so what is the extent of reaction for this reaction? You can easily get it, what is the extent of reaction, because you know every component that is being formed. If you're going to, it's so obvious. You don't even need to do the table. You don't need to construct the table in order to know what is the extent of reaction. Anybody? Can anybody give me what is the extent of reaction? For this example, for this problem, what is the extent of reaction? Your reactant,
1 more.
1 mole. Why?
It is the form that has been consumed to form the product.
What is being consumed? What, can you specify what is being consumed, please, Ibrahim?
Well, actually, the limit reactant here is not known because they have the same. I guess both the reactant are limiting. So
Yes.
because they have 1 to 1.
Yes. 2 to 1.
Yeah, but if you divide it out, like the amount of in
Sorry?
the amount of NH3 entering the system divided by its coefficient, it will be 1. And
Yes.
so the limit reactant is not obvious here, but I
Both,
guess,
both of them are limiting.
yeah. So this is why the extent is 1.
Okay, there's another way of looking at it. Just look at the product. Okay, I know what you're trying to say. Both of the reactant, they are being consumed, right? So both of the reactant are being consumed. So just look at one reactant, for example. Look at sulfuric acid solution. If 1 mole of sulfuric acid is being 1 mole of sulfuric acid is being supplied, and 1 mole of sulfuric acid is also being consumed, so that means your extent of reaction is going to be 1. That's another way of looking at it. Or you look at the product. Initially, there is no ammonia sulfate. Initially, there is no ammonia sulfate in your input. You produce 1 mole of ammonium sulfate in your output. So that means you have, since the coefficient is 1, that means your extent of reaction is also 1. Get it? Anybody? Is that clear? Good, thank you. So your extent of reaction, you don't need to construct the table. You can just look at the equation and you know that it's going to be 1 because it's per mole of the ammonium sulfate being formed. Initially, there is no ammonium sulfate at all in the feed. Now you form 1. And if you look at the stoichiometric coefficient, that is also 1. So it's just, if you want to use the formula, what is the formula? Remember, you have this plus minus initially, but we're not going to put it there because we are looking at the product. Okay? And in minus N out. Is it N in minus N out? Anybody? Do you know what is the formula?
Yeah, I think it's N in minus N divided by the stoichiometric coefficient.
Okay. Amount of product, if you're looking at product, or amount of reactant, if you're looking at reactant, consumed divided by its stoichiometric coefficient of that reactant, okay? Or another way of looking at it is looking at the sorry, I got my god. Okay. I don't want that. I'm going to erase this. Okay. Is looking at the product, amount of product produced, that's another way of looking at it, divided by that product's coefficient, So let's look at one of it. For example, we look at the amount of product which is ammonium sulfate. So our ammonium sulfate that is being produced 1 mole, divided by its coefficient. Based on this equation, the coefficient is 1. So 1 divided by 1, you end up with 1 mole. Okay, that is your extent of reaction. So, but if you want to look at in terms of one of the reactant, have a look at one of the reactant. For example, look at ammonia. You have 2 mole of ammonia being consumed. Why is 2 mole of ammonia being consumed? Because none of it is coming out. It is completely consumed. So 2 mole of ammonia divided by the coefficient of ammonia, according to the equation, it is 2. You end up with 1. Still the same. You have the same extent of reaction. Or if you want to use that of the other reactant, which is sulfuric acid, you have 1 mole of sulfuric acid being formed, and the coefficient of sulfuric acid is 1. So 1 divided by 1, you end up with 1. So you still get the same extent of reaction. If you want to write down the equation, this is the equation. But you can easily look at it from the equation. You can know that the extent of reaction is going to be 1 because your product is going to be formed 1 mole and the coefficient is also 1. So obviously it's going to be 1 mole. So that is your extent of reaction. Now we need to find the heat of reaction for that reaction. Yeah? You already know what's the number of mole. You need to find the enthalpy here, enthalpy there, and enthalpy here, enthalpy 3. So before you can proceed, you need to state your reference state. So the reference state, whenever you have a heat of reaction, you can find it. You can use a different temperature, but then you just make it longer because you need the hypothetical path in order to get it at a different temperature. But if you state it at 25 degrees C, since your heat of reaction is at 25 degrees C, so it's easier that way. So you're going to use the compound as your reference state because we are using the heat of reaction. So we're going to have ammonia gas. We're going to have sulfuric acid solution, aqueous, and you're going to have your compound, the product, which is ammonium sulfate. So let's look at the formula. NH4 then you have sulfate, that's 4. That's going to be aqueous. And all of it is at 25 degrees C. All of this compound is at 25 degrees C, 1 atm. So that's your reference state. You need to specify a reference state before you can proceed to do the calculation of the enthalpies. Okay, so now let's get the heats of, let's see, if you want to draw the table, no problem. If you don't want to draw the table, in this case, I don't see the need of doing the table. Okay, since we already know that the reference state is at 25 degrees C, 1 atm, you're looking at the compound. So now look at the block diagram. Here it is at 75. So this is not going to be 0 because it is not at 25. Over here it is at 25. So that enthalpy is going to be 0. Then the same thing for your product, it is at 25, so that is going to be 0. So you need to find this enthalpy for your ammonia. That's the only value that you need to find in order to calculate Q. Another value that you need to calculate, of course, is the heat of reaction. Okay, so now let me erase this because you're going to calculate a value there for the first for the enthalpy of ammonia. For the other two, for the product for sulfuric acid solution, and for the sodium ammonium sulfate, it is 0 because they are at the same reference state. The temperature is at the same reference state. The compound is the reference state. It's not the element, it's the compound. So that's done. You only need one of these. So what you have to do for this part, because you start at 25 degrees C as your reference state, you need to get the enthalpy using the Cp of ammonia gas, which you can get the polynomial equation from appendix B2. You need to do the integration. Okay? So, but first, let's get the heat of reaction first. Since the equation is very far up there, so I'm going to rewrite the equation. So where is the equation? You have 2 mole of ammonia gas reacting with 1 mole. I don't need to write the 1 mole sulfuric acid equals. You're going to assume that that is going to be dilute, because not really assume, it's already mentioned that it's dilute. So you're going to say R is equals to infinity. Going to form ammonium sulfate, and that is going to be aqueous. For your heat of reaction, according to the heat of formation, is going to be product, thermometric coefficient, heat of formation, minus reactant, thermometric coefficient, and the heat of formation of your reactant. So let's list down what do we have for the product. We have the stoichiometric coefficient is 1, so I'm not going to write that as 1. For heat of formation of your aqueous product, NH4 sodium sulfate, aqueous, minus your reactant. We have ammonia gas. So there's 2 mole of ammonia gas. So that's 2 times by the heat of formation of ammonia gas. Can get that directly from appendix B1. Plus the heat of formation, the coefficient in front of sulfuric acid is 1. So I'm not going to write 1 there. I'm going to straight away write the heat of formation of my sulfuric acid aqueous. Okay. The aqueous implies that R equals to infinity. It's also R equals to infinity. If you want to write it, no problem. Just write here, aqueous R equals to infinity. Okay. If you want to be, just in order to be clear about it, erase please. Okay, that is going to be aqueous R equals to infinity. So that you know, whenever you need in order to get the, for example, the heat of formation of that solution, or for example, NH4, I'm not sure whether you can get it directly. So let's do the sulfuric acid first, because we have the heat of mixing from appendix B11. So let's do the sulfuric acid. H2SO4 aqueous. Let's write the R. That is equals to heat of formation of your sulfuric acid liquid, plus the heat of mixing. R equals to infinity. Yeah. If you need that information, that if it's not given in appendix B1, then you'll be using this equation. So let's look at appendix B1, whether it is available at the infinite dilution for sulfuric acid and the product. Let's look at appendix B1. Sulfuric acid. Yeah, there is our sulfuric acid. Do we have the aqueous? Oh, good, we do. That's it. We don't need to calculate it. It's already given. Minus 907.51. Okay, so just list that down. That is your heat of formation of the aqueous solution. We'll go back to our example. So this whole thing is going to be minus 907.51. We did this earlier, if I'm not mistaken, the calculation. Let's look at this example. We did this example earlier. There you go. We did it earlier. Okay. That is how you get your value minus 907.51 if it's not available in appendix B1. This is how you do the calculation. Okay, you get the heat of formation of your liquid sulfuric acid plus the mixing at infinite dilution. That is the same value as the one given in appendix B1. Okay, so if you have to calculate it, this is how you do the calculation. But since it's already available in appendix B1, so we're just going to write down that value in our example or in our problem here. So that is kilojoules per mole of your sulfuric acid, your solute, which is liquid. Okay, so that's one value. Next, we're going to look up for heat of formation of your product, which is ammonia sulfate aqueous. So whether it's available, let's have a look in appendix B1. Ammonia sulfate. That will be somewhere at the very top here. Ammonium sulfate, guys, I just saw it. It's here. Okay, so let's see. Yeah, this is the value. Right, you have for the crystal, that's the crystal, but we are looking at the solution. So it's minus 1173.1 kilojoules per mole of ammonium sulfate. So I'm going to write that down in this example, in this problem, minus 1173.1 kilojoules per mole of your ammonium sulfate. SO4. Right? So that's done. Next, what do we need? We have that done. We have this. We have this done. We need to get the ammonia gas, the heat of formation of ammonia gas. Again, we need to look it up in appendix B1. We're going to go to appendix B1 for ammonia. Where is ammonia? So ammonia is here. Better highlight it. This is ammonia. Yeah, for your gas, you have liquid, that's gas. It's minus 46.19 for ammonia gas. That's the heat of formation of ammonia gas. So let's go back to that problem and write down minus 46.19 for the heat of formation of ammonia. Okay, so now if I just use my highlighter to point out, this is the heat of formation that you're going to put there, substitute there. This is your heat of formation. Sorry guys, I got it wrong. Okay, this is your sulfuric acid. That is sulfuric acid. Okay? This is for your product. I'm going to put it, substitute it there. And lastly, it is your ammonia. We're going to substitute it there. Okay. Now let's do the substitution. The heat of reaction is equals to your product, heat of formation of your product, minus 1173.1 minus the reactant. This is your product. The reactant is 2, that of ammonia, minus 46.19 plus that of sulfuric acid, minus 907.51. Then, so you have calculated it, we should be getting the heat of reaction. What is the heat of reaction, guys? Somebody calculate. Obviously, it is minus. Anybody? Do the calculation, please. What is the heat of reaction? Anybody? No? Nobody going to calculate it? I get 173.21.
Yes, those are the same.
Thank you very much. That is your heat of reaction. That is not the that's not the unknown that is requested for. We're supposed to find Q is equal to extent of reaction times by heat of formation, heat of reaction, plus I'm repeating myself again. That minus in. Okay, now we have one more calculation that we need, two more calculation that we need to do. We need to calculate this enthalpy H1. Then we need to calculate that. What is H1? So if you look at up in appendix B2 for ammonia, the polynomial equation, if you look it up, okay, from 25 degrees C, because that is your reference state, your reference temperature, to 75, that's the temperature of the input of your ammonia. If you look it up, this is your value of A. Remember to have a look at whether the form is 1 or 2 and what is the unit of your temperature. It's very important because some of the values given in appendix B2 is not in degree C. It is not in, it is in Kelvin. It's not in degree C. It is in Kelvin. Then you need to change your temperature, the unit of your temperature. And also it might not be in using form 1, it could be form 2. Be careful on that. Now I'm just writing down the coefficient of the polynomial equation to get the enthalpy for ammonia. This you can get from the appendix B2. So you should be very familiar with that appendix. We have done a lot of calculation using it. So if you do the integration, I got my value is 1.832 kilojoules per mole. Okay, so that is my enthalpy 1. So I'm going to write that down in my block diagram, 1.832. So if you come up with a different answer, please tell me. And that is going to be 1.832. Okay. So now everything is there except to calculate for your Q. So we're going to substitute these values inside our final equation. And that is our final equation. So Q is equals to your X mole, 1 mole. I'm not going to write down the unit. I'm just going to write the extent of reaction. Your heat of reaction minus 173.21. We calculated that earlier. So now for the out, you have 1 mole coming out, but the enthalpy is 0. That's 0. That's the 1 mole coming out times by that is enthalpy, that is 0. 1 times by 0. Don't really need that bracket, but I'm just going to stick with that bracket. Okay. Now the reactant, the input. For this input, I have 2 mole of ammonia, and that's my enthalpy. So 2 times by 1.832. Okay, plus my other reactant, my other input, which is 1 mole of sulfuric acid, but the enthalpy is 0. 1 times by 0. If you do the calculation, your amount of heat, you should get minus 176.874 kilojoules. That's the final value for the heat that need to be, that's going to be released. It's going to be released from your process unit, minus 176.874. Okay, anybody getting a different answer? Okay, assuming that everybody is getting the same answer. Okay, so that is using the method of heat of reaction. So if you're going to use the heat of formation method, your heat of reaction is still the same, but you're not going to use it at all. So the equation Q is equals to out and enthalpy minus in your number of mole and the enthalpy. But your reference state is going to be different. Your reference state, since you're going to use the heat of formation, your reference state is going to be the elements. So what elements do we have? Look at the equation. The equation is over here. Yeah, that's the equation. You have ammonia, so that means here you need nitrogen gas. You need hydrogen gas to form ammonia. You need hydrogen gas. You need sulfur solid. You need oxygen gas. Right? For here, nitrogen gas, hydrogen gas, sulfur solid, oxygen gas. So you only have four elements that you need to use at 25 degrees C. So your elements, there are ammonia gas, because it occurs naturally in that form, hydrogen gas, oxygen gas, and sulfur in a solid form at 25 degrees C and 1 atm. Okay, so that is your reference state. So now, you need to form your first ammonia. Initially, your ammonia gas, you need to form it. So you start with a nitrogen gas and hydrogen gas in order to get ammonia at 25 degrees C. So you go from this starting point to your ammonia. You form it first, your ammonia gas at 25 degrees C. But your ammonia that we have initially is not at 25 degrees C. Your ammonia is at 75 degrees C. So you need to heat it up. Once it has been formed as ammonia, you need to heat it up from 25 to 75. You're going to go from 25 to 75. So over here, your enthalpy is 0 because that is your starting point. Your enthalpy over here is going to be this is going to be, you're going to form it first, the heat of formation of ammonia. Okay? And over here, you're going to integrate from 25 to 75, the Cp of ammonia. That is the heating part. Yeah? So this is the final, your how to get your enthalpy for ammonia. So in this case, we use the same symbol. Just now we use H1. Yeah, so we're going to use H1. So your H1 is going to be H1. Okay, so H1 is going to be the formation of ammonia first, ammonia gas, then the integration or the heating part. Okay, the heat of formation of ammonia. Do we have that information here? We can get it from Appendix B1. Heat of formation of ammonia, do we have it here, guys? There you go, you are. Isn't it? We got it earlier when we wanted to calculate the heat of reaction. Okay, that is the heat of formation of ammonia gas. It's minus 46.19. I'm going to substitute that value here. Your integration just now, we also did that integration earlier. We got 1.832. So plus 1.832. So you will get a value of what? For ammonia, I got minus 44.36 kilojoules per mole. Okay? So that is H1. For H2, it's not going to be 0. Why H2 is not going to be 0? Because you are starting from the elements. When you start with the compound, then it becomes 0. But if it's not, you're not starting from this compound. You're starting from the element which is hydrogen gas, sulfur solid, oxygen gas. So you're going to calculate it. You need to form it first. Okay, so you do the same thing as what we have done for ammonia. So you start with your hydrogen gas, with your sulfur solid, and your oxygen gas. So that is at 25 degrees C. You form your sulfuric acid liquid. Or aqueous. Sorry, it's not. It's aqueous. It's not liquid. It's aqueous because the equation is aqueous. Yeah, it's not liquid. So this is your heat of formation of your solution of aqueous, which is your sulfuric acid, aqueous at infinite dilution. Yeah, so you already managed to get that value actually. Where is that value? Over here. That is the value. Yeah, the heat of formation minus 907.51. That equals to minus, this is H2, minus 907.51 kilojoules per mole. This is actually the same as part A, the heat of reaction method. Next, H3. H3 is the product. So you start from, in order to form your product is ammonia. What's the formula? Let me look at the formula. Ammonia, H2O, sulfate, aqueous. That is your product. So we're going to start from, this is at 25 degrees C. This is also at 25 degrees C. So you start with nitrogen gas, hydrogen gas, and sulfur solid, and oxygen gas at 25 degrees C. So you start from your element, you're going to end up with your product. So this is going to be aqueous. So that is your heat of formation of your product. And H4, 2, SO4, aqueous, R equals to infinite. So you already have that information actually when you did the calculation for the heat of reaction. And that is the value that we got from appendix B1. So that is minus 1173.1. So put that value there. That is equals to H3, 1173.1. So now, for this example, if you want to construct the table, you can do so because you have the values for all three components. I'm just going to go through this very quickly because it's almost time up. This is N in, that is the mole. Yeah. Enthalpy in, that is kilojoules per mole. N out, mole. And lastly, enthalpy out, kilojoules per mole. Yeah. So write down the number of mole that we have for ammonia coming in. You have 2 mole. For your sulfuric acid, you have 1 mole, that's aqueous. For your product, ammonia sulfate, that's also aqueous. Don't have it in the feed, but you do have the amount coming out, 1 mole. So the value that we have just now, we have minus 44.36, minus 907.51 for the enthalpy that we just got just now, minus 1173.1. So if you do the final calculation using the heat of formation, out minus in, I'm rushing through. So let's do it. Minus 1173.1, so that's your out, minus your in. Okay, so close the bracket. You will end up with the same value as what we got earlier for the heat of reaction method. Same value. No different. Except that if you do this method, well, you have to start from elements. If you're using the heat of formation method, you're going to start from elements. So any questions? It's almost time up. We have about 4 minutes if you want to ask anything. Any questions? Which one easier? It's up to you guys. I think both of them is you will still require the same amount of work. It's just that for the second part, using heat of formation, because the information is already available when we did it using the heat of reaction, so it looked as if it's faster, but actually you still have to go the extra length of looking it up in appendix B1 and B2, the integration. Any questions? This is problem 944. This is how you use the information of the heat of formation of solution. because you are producing, your input is solution, your product is also a solution. Any questions? Anybody? Everybody too tired? Too many things that you just too tired? You have gone through with the mini project, you have other project with other subjects. It's quite heavy, that learning online. Sometimes the internet is not that good. Sometimes you just cannot follow using online, studying online. You're just so sleepy, too tired. So I hope you guys, if you cannot follow this, have a look at, try to do it yourself and see whether you come up with the same answer. Okay, guys, since there's no questions, we will continue with this topic tomorrow. And if I have the time, I will set one quiz for you guys to take by tomorrow, so that you have 2 quizzes for 5%. For 5% mark, 2 quizzes. Okay, guys. So what quiz am I going to ask? Well, most probably in what we have covered today and last week. Yeah. So the quiz will be what we have covered today and what we have covered last week. So last week was heat of mixing and solution. Today, how to calculate Q. But let's just something simple. It will not take you that long, maybe 15 minutes to solve it. Okay, guys. So thank you very much. If there's no questions, if anybody requests for me to show the QR code, I will do so. But if there's no request, then that's it. So, Assalamualaikum warahmatullahi wabarakatuh.
Salam. Thank you, Dr.
Welcome.
Thank you, Doctor.
Welcome. Nobody going to reply to my salam?
Waalaikumsalam.
Thank you very much. I need that.